Depending upon the number of carbon atoms, monosaccharides can be classified into these categories. Basically, we can have trios if there are 3 carbon atoms. Example would be glyceraldehyde. They can be tetroses if they have 4 carbon atoms. Example would be erythrose. They can be pentoses. Example would be ribose. They can be hexoses. Example glucose, fructose. So we have seen the glucose structure. It has 6 carbon atoms. 1, 2, 3, 4, 5 and 6. That is why it is a hexose. I have mentioned here it is a hexose. We can have 7 heptoses, pseudoheptulase and nonoses, for example neuraminic acid. So that is how monosaccharides can be classified. Okay, and other than erythrose, we can also have another example over here, threose. Okay, and other than ribose, we can also have another example, which is xylose. And in heptoses, other than pseudoheptulose, we can also have another example, glucoheptose. Okay, now another important aspect of this is the glycosidic bond. Okay, glycosidic bond. What are glycosidic bonds? You see, the aldose or ketose group present inside carbohydrates, which I have already shown you, they can react with alcoholic or nitrogen group of another organic compound, and that bond will be a glycosidic bond. So the bond can be COC or the bond can be CNC. And glycosidic bonds are also established when we are condensing more than one monosaccharides, and that will lead to the formation of oligosaccharides and polysaccharides. So this also we can mention as a point, that during condensation of 2 monosaccharides into oligo or polysaccharides, hydrolysis will happen. That means there would be a release of water molecule, and on account of establishment of such bonds, or rather whatever is the resultant bond, due to this dehydration, because a water molecule is lost and at the same time a new product has been synthesized, so dehydration synthesis, the bond which is formed, the resultant bond, will also be a glycosidic bond. In the later classes, when we talk or when we discuss the bonds or discuss the molecular structure of these organic compounds, this will be a much clearer concept then. But till now you should know that whenever we are condensing, that means it is kind of an anabolic process. We are adding 2 molecules and forming a bigger molecule. That is why monosaccharides get add up to form oligosaccharides or polysaccharides, and that is leading to a release of water molecules. So there is a dehydration process and at the same time a synthesis process. Resultant bond would be the glycosidic bond. So monosaccharides are the monomers. They cannot be further divided. Derived monosaccharides will have something other than carbon, hydrogen, oxygen. They will have certain extra things to them. And oligosaccharides would be again made of monomers. They can be divided into monomers actually. Polysaccharides, they are much larger carbohydrates. They are made up of, they are actually polymers. From the word itself we can understand they are polymers. And in today's lesson, since we will concentrate on monosaccharides, I'll not be talking much about other sugars. Anyway, so let us come to glucose. So usually these pentoses and hexoses, see, pentoses and hexoses, so they exist in both open chains as well as ring forms. And there are two types of ring forms, pyranose and furanose. Okay, so both of them exist in open chain as well as ring form. Now this ring form has got two types, pyranose and furanose. So pyranose has hexagon structure with 5 atoms and 1 oxygen, and furanose has got pentagon structure with 4 carbon atoms and 1 oxygen. So hexagon 6 sided, so they have 5 C atom and 1 oxygen atom, and these are pentagon 5 sided, they have 4 carbon atom and 1 oxygen atom. Again, these have both pyranose and furanose types. They are further distinguished into alpha and beta forms. Okay, they can further be distinguished into alpha and beta configurations. So in alpha form, we say that the hydroxyl group nearer the oxygen atom of the ring, that will be written below, while in beta form it is written above. Okay, like in this particular diagram you see the hydroxyl group which is nearer to the oxygen, that means this one, this hydroxyl group, so this is written below, so this will be an alpha form, so that is why I have written alpha ring form. Pyranose obviously because it shows a ring structure which is a hexagon, because 6 sided, 1 2 3 4 5 6, and it has got 5 carbon atoms and 1 oxygen atom. This is the 1 oxygen atom, and 1 2 3 4 5 carbon atoms, actually 6 carbon atoms altogether, but anyway you get the point. So 1 2 3 4 5 and 6, that is our 6. But the point was, since the hydroxyl group which is the nearest hydroxyl group to oxygen atom, this is not the nearest, because you see immediately next to it there is one carbon atom, and then again there is another carbon atom, but this one is the nearest, or rather the most adjacent hydroxyl group, and since it is below to this plane of reference, so this would be an alpha ring. In case of beta rings, this would have been above. That is the thing. So we have alpha and beta configuration, which are shown in both pyranose and furanose. Okay, and many monosaccharides, they have asymmetric carbons, and we know asymmetric carbons which are usually denoted like this. So what are asymmetric carbons? We know that the carbon has a valency of 4, so every side will have a different value. No two side will be same with respect to this carbon. So this would be the asymmetric carbon denoted by star. And asymmetric carbons, they have the capacity, or they have the ability to rotate polarized light. Okay, so here I am writing asymmetric carbon can rotate polarized light. And depending upon the degree of rotation, that means whether they are rotated right side or left side, there is another configuration or nomenclature which we follow. So if the polarized light is rotated right towards right side, then it would be denoted as D or plus. So this is dextro-rotatory. And if it is rotated towards left side or negative, then it would be levorotatory. Okay. And usually we see that amongst sugars, D isomers are more common. These all are isomers, that means they have the same molecular formula, but their spatial configuration or their spatial arrangement, their geometric configuration, or rather optical ability, optical configuration, there is difference in those intricate things. Otherwise, their molecular formula overall would be same. So most amongst sugars, D isomers are more common. Okay, so this is what we learned today. We learned today about monosaccharides, which are the simplest monomers. They cannot be hydrolyzed further, and there are roughly 5 types, though we have studied more than 5 types depending upon the number of carbon atoms. They can be trioses, tetroses, pentoses, hexoses, heptoses, or nanoses, and they form glycosidic bond. Basically, the carbon atoms, they are forming the glycosidic bonds. They undergo condensation, and through condensation they form oligosaccharides and polysaccharides, and that would also be named as a dehydration synthesis process. And pentoses and hexoses, they are found in rings also, along with open chains. And rings can be pyranose or furanose, and again pyranose, furanose rings can have alpha or beta configuration. And then again, alpha beta configuration can also have a D or L form, like this thing. They can be D or L. So this is all about today. Thank you guys. Stay safe and subscribe our channel IB360.